This is a recording of the second half of the 6-1 lecture. We'll be focusing on the mean and the standard deviation of a discrete random variable, and we'll do a little bit of definitions and definitional work having to do with continuous random variables. Um, we'll start with that mean of a discrete random variable. A discrete random variable, as you recall, has uh, a bunch of outcomes that have gaps in between. And for each one of those outcomes, there's a probability associated with it. If we want to find the mean, which is also sometimes called the expected value, we take the data value, x, and we multiply it times its corresponding probability, p. And we'll add up all of those products and we'll get the expected value. Let's take a look at this through the lens of the data set that we looked at in the previous recording, and that has to do with NHL goals during the 2010 hockey season. It says, here are the goals scored by the teams and the probability that those number of goals had been scored. It says, compute the mean of the random variable x. Well, that mean, or the, again, expected value, is going to be a data value like 0 multiplied by a probability like 0.061. And then we're going to do this for every combination of goals scored with their corresponding probabilities. Let's do 4 times its probability. Let's do 5 times its probability. 6 times the 4.1% probability there. 7 times the 1.5% probability. 8 times the 0.4%. Very rare we get. Let's do 4 times its probability. Let's do 5 times its probability. 6 times the 4.1% probability there. 7 times the 1.5% probability. 8 times the 0.4%. Very rare we get 8 goals scored in a game, and it's even more rare to get 9 goals scored in a game. Now, I'm not even going to pretend to try to add those numbers up, multiply them out. So I'm going to go and switch over to my calculator. I'm going to start a new document on my calculator. And let's go ahead and let's type in all those values. So 0 times 0.061 plus 1 times 0.51. About 15% with those one goals scored for the game. 3 goals. 4 goals. 5 goals. Put that down a little bit. Oops. Need to go back and be in the calculator when I hit these buttons. There we go. 6 goals. 7 goals. 8 goals. And then 9 goals. And we get that value ends up being 2.851. The units here are goals, and that is the computing. But it also asks us to interpret this value. All right? Well, what does it mean to interpret this value? It means that over the course of many NHL games, I'll put the word average there, the average number of goals scored is 2.851 goals. Now you're like, of course, how do you interpret the average? You say that the average. Well, the key here is that we mean this number only over the course of many games. In the same way that we think that only over the course of many trials do we think the probability has a particular value. How about the standard deviation? Well, in the standard deviation calculation, we know already that the standard deviation is the approximate average distance from the mean. Our calculation, we will take data values and subtract it by the mean. We'll square it, which will create a positive number, and then we will weight it by multiplying it by the probability. Now, this particular equation gets you the variance of x. And if you want the standard deviation, you need to take the square root of the variance. Again, let's take a look at this um, under the uh, under the lens of this data set. Now remember, we've already established that the average number is 2.851. Well, that means the variance of x, again, sometimes also sigma x squared, is going to be data minus 2.851, the mean, squared, and then weighted by the probability. 1 minus 2.8, 2.851 squared, again, multiplied by the probability. And we'll do one more on this line, 2 minus 2.851 squared, and then multiply this by 0.228. Okay, more data values. Oh, the next one's 3, not 5. 2.851 squared multiplied by its corresponding probability plus 4 minus 2.851 squared times its probability 0.173 plus 5 minus 2.851 squared times its probability 0.094 onto 6 and its probability onto 7 and its probability 8 and its probability. And then lastly, 9 and its probability. All right, so there's our formula. There's me showing all the work to get this. And do we expect you to show work? Yes, we do. Let's bring up the calculator. And now I get the unenviable task of indeed plugging in all that. 2.851, close the parenthesis, square it, and then multiply it by the probability. One down. Times the probability. And okay, 2 down. Make sure I can see the next line. So this is going to be, oops, did it again. Get back over here onto 2. Oh, got an extra decimal place there. Let's get rid of that. Square that and multiply that by probability of getting exactly 2 goals. In parentheses, 3 minus 2.851 times, or to the second power, and then multiply the probability of 3 goals. One more time, but this time for 4. And we'll square that and multiply by it. Okay, on to 5. Okay, square that. Oops, too many squares. There we go, corrected that. And this is probability of 5. And let's do 6. Multiply by the probability of 6. 7. Add that, or multiply that. Probability of 7. And now 8. And probability of 8. And then lastly, 9. Square that. And then multiply it by the probability of the 9. Now, I hope I got all those in right. And when I do this, I get 2.6648. Minimize that. And again, that's the variance. But what about the standard deviation? The standard deviation is the square root of that variance. For that, I need to go back to the calculator and I will say square root of that number, and I get that, which is 1.63242, and that unit is in goals. There's the compute part done. What about the interpret? Our interpretation of that is over the course of many NHL games, the average distance of goals scored to the mean is 1.632, and the unit here is goals. All right. Now, if you went through this process between watching me do either of these and you said, well, that seems arduous, you would be right. You would be absolutely right. If you said to yourself, gosh, I bet you there's an easier way to do this, you would be right. And the way to do this on the TI calculator is in this technology corner page, and I will talk you through it right now. First of all, let me maximize this and give a big side screen, and we can talk about how we would do this in a simpler way. And it starts off with us creating a page, which is going to be a page in which we put data and statistics. Oops, sorry. I meant to add a page. It's going to be a list and spreadsheet page. Now, in this list and spreadsheet page, we're going to have two columns, one with the actual data. It's called goals for this particular one. And we put in the different values that the discrete random variable takes on, right? In the second column, we'll put in the probabilities for each of those goals. And I'll just put in the data or those probabilities. 5. This is the one for 6. This is the one for 7. This is the one for 8. And this is the one for 9. So now we have these two lists, essentially the probability model, the values that the discrete random variable takes on, and how often it takes on those variables. Now, what do we do with that? Well, let me add a calculator page to this document. We can go to menu, and under statistics, stat calculations, one variable statistics, we ask you how many lists. Well, there's only one data list, and that's the one called goals. So one data list, so one. What is the name of that data list? It's called goals. And how often do we have goals? Well, those are the data, but that's the information that's stored in probabilities. So if we put in goals and probabilities in those two fields, we can see that one, it calculated the 2.851 as the average number of goals, and it calculated the 1.632 as the standard deviation. So if we just put all the information into two lists, we can get the calculator to spit out that information. All right. So given that, let's go on to the next example problem. Let's do this calculation both ways, um, knowing that we're not often asked to do it by hand, but we are asked to show our work. So in this case, a large auto dealership keeps track of sales made during each hour of the day. Let X be the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. Compute and interpret the mean of X by hand. So the mean of X, or the expected value of X, is equal to data value multiplied by probability plus a data value multiplied by probability plus a data value multiplied by probability plus data value multiplied by probability. Now, if I multiply this out, 0 times 0.03, that's 0. 1 times 0.4, that's 0.4, plus 2 times 0.2 is 0.4. And then lastly, 3 times 0.1 is 0.3. And if I add 4 plus 4 plus 3, I get 11. And with the decimal point, I get 1.1. And the unit here is cars. And remember, cars in this case provide some context to our answer. But what about the interpret? Well, over many, in this case, Fridays, the average number of cars sold is 1.1 cars. And again, don't forget that very important phrase. All right, let's see if we can calculate the standard deviation by hand. Remember, first we're going to calculate the variance, which is sometimes, again, sigma squared of x. And it is a data value minus a mean squared multiplied or weighted by that probability. One more time. Data value minus a mean squared multiplied by or weighted by a probability plus data value minus mean squared multiplied by probability. And lastly, data value minus mean squared times probability. Let's see, I got 1.1 squared. I think that is 1.2. We're going to multiply that by 0.3. I've got negative 0.9. No, sorry, negative 0.1 squared. Well, that's 0.01 multiplied by 4, 0.4. 0.9 squared is 0.81 times 0.2. And then this ends up being 0.19 squared. 1.9 squared. So 9 times 9 is 81, carry 171, and then 19, 1, 6, 361, and I've got two decimal places. So this ends up being 3.61 times 0.1. Okay, now multiplying these two together, this is going to be 363. 363 with three decimal places there. All right. This is going to be 4 with three decimal places. This is going to be 162 with three decimal places. And then move the decimal place one more time for there. And if I add these up, let's see, 3 plus 4 is 7, plus 2 is 9, plus 1 is 0, carry the 1, 7, plus 6 is 13, plus another 6 is 19, carry the 1, 4, 5, 8. So I'm going to get 0.890 for the variance, but the standard deviation of x will be the square root of that number. And that, my friends, I cannot do in my head. So I'll go back to the calculator and I'll ask, what is the square root of 0.9890? And I get 343, 0.943. 0.943. That handles the compute part. But what about the interpret? Well, um, for the interpret, it's going to be, again, over the course of many Fridays, the average distance to the mean number of cars sold is 0.943 cars. All right, so we worked really hard to do this by hand. Let's try this out on the technology. So let's go back to our calculator. I'm going to create a new page. Actually, I'm going to create a whole new document. Let's get rid of all that other work. No, I don't want to save that. Right? So I'm going to have a list and spreadsheet page. I'm going to put in this column cars, and this is the number of different cars sold, which range from 0 to 3. I'm going to put in here probs, and here are the probabilities for each of those particular outcomes. All right, and then I'm going to add a page. It's going to be a calculator page, and I'm going to go menu, statistics, stat calculations, one variable statistics. I only have one data list. It's called cars. I only have one probability list. It's called probs. And we'll scroll up a little bit just to confirm that, yes, we have 1.1 on average and 9.43 for our standard deviation. You can see it's sigma of x, the standard deviation right there. All right. So we've checked that and it works out. Check. All right. Now, switching gears. In a discrete probability distribution, we can enumerate all the possibilities that the random variable takes on. But in a continuous random variable, there are no gaps between. And which means that in between outcomes, okay, let's say our data set are all possible numbers between 0 and 1. Well, how many different numbers are there between 0 and 1? And the answer is there's an infinite number. There's a half, there's a quarter, there's an eighth, there's a 16th, there's a 32nd. I can keep on going on and on. There's an infinite number of numbers in that range. Well, I can't list out all of those infinite outcomes. So what are we to do? Well, what we are going to do is we are going to show the particular outcomes not as a list, but as a graph. And that graph is what we talked about in an earlier chapter, and it's called a density curve. Okay, so for example, let's say we had a density curve, and this drawing is kind of small. Let's say it's a uniform density curve, which means all outcomes are equally likely, and the outcomes range from 0 to 1, and all outcomes are equally likely. So we have this density curve. Now, how tall is this curve? This curve has to be 1 because the area under the curve must represent all possible outcomes, which are with a probability of 1. And now we ask the question, like, if this is the density curve, what's the probability of being between, let's say, zero point 0.3 and zero point 0.7? Well, the answer to that question is that we go between zero point 0.3 and zero point 0.7, and we go up to the curve, and we say, well, how much area is in that curve? Well, this rectangle has a height of 1, and this rectangle has a width of 0.7 minus zero point 0.3 of 0.4. And because zero point 0.4 times 1 is 0.4, we say that the probability of this outcome is 0.4. And that's how we deal with continuous random variables. So let's see if we can get a little summary here. A continuous random variable x takes on all the values in an interval of values. The probability distribution is described by a density curve, again, because we can't list out all the possibilities. The probability of an event is the area under the density curve and above the values of x that make up the event. Okay? Now, continuous random variables have infinitely many possible values. It says that we are going to define that the probability of any one event, let's say in that previous example, the probability that y is exactly 0.5. If I go back to that drawing, I said, well, where's 0.5? It's right here. Where's the outcome 0.5? It's that line at 0.5. How much area is in that line? And the answer, the area is 0. We say that the probability of getting exactly 0.5 is 0 because it's just one of an infinitely many results. Okay, but if you're on an interval, then you may have a probability to say, again, only intervals can have positive probabilities. What's the most common density curve? And the answer is that it is the normal distribution. So let's say we have a situation where we have a normal distribution for the heights of young women, and the mean is 64 and the standard deviation is 2.7. Now you choose one young woman at random, call her height y. If you repeat the random choices many times, you get the same normal distribution. Find the probability that the chosen woman is between 68 and 70 inches tall. So first of all, the height y is again part of a normal distribution with a mean of 64 and a standard deviation of 2.7. Let me write that again. Y is a normal distribution with a mean of 64 and a standard deviation of 2.7. Or we can draw it out. Here's a not too bad normal distribution drawn out with a mean of 64. This distance from the middle to the point of inflection is 2.7, which means that this is 66.7. Another standard deviation up will take me to 69.4, I think. If I go a standard deviation down, that's going to be 61.3, I think. And I go one more standard deviation down, and I think that's going to be like 58.6, right? We're asked to find the probability that the random variable y sits between 68 inches and 70 inches tall. In other words, what's the probability that I'm between 68, which is about here, and 70, which is about here? That area right there. We're wondering what is the probability that y is between 68 and 70 inches tall. Now, one way to solve this is to go and find the standardized heights. So what is the standardized height for a woman who's 68 inches tall? Well, that's 68 minus 64 divided by 2.7. Let me bring this calculator back. Let me just do the handheld only. Take in front. Just over here so we can see it. Make it nice and big. All right. And let's go ahead and I'm going to hit Control Division to get the fraction 68 minus 64 divided by 2.7. And we get that this is 1.48148. Now we're only really going to use these 3 decimal places. What about the standard score for the high end? 70 minus 64 over 2.7. And again, I'll go over to the calculator, control division to get the fraction. 70 minus 64 divided by 2.7. I hit enter, and I get 2.22. All right, so what do we do with that? Well, the probability that the y value, the random variable value, is between 68 and 70 is the same as the probability that the z value is between 1.48 and 2.22. Now, this is a high minus low problem, if you remember that from an earlier lesson, where we're going to look up the probability of 2.22. And I happen to have a z table ready to go for us to look that up. And we'll go to 2.22 on the table. So I can look at 2.2 and then down, and I get 0.9868, 0.9868, and then I'm going to do the same for the 1.48. So I go to 1.4. Let's get this calculator out of the way. 1.48, and that looks like 6 or 0.9306, 0.9306. 6 minus, or 8 minus 6 is 2. 6 minus 0 is 6. 8 minus 3 is 5. 9 minus 9 is 0. So it looks like we've got about a 5.62 probability of getting a woman between 68 inches and 70 inches tall. Now that's doing it all by hand and using the table. Let's not forget that we can do this on the calculator as well. What does that look like? Well, this probability that we're interested in ends up being a norm. Helps if you spell it right. A norm CDF. Okay, let's take a look at what that looks like on the calculator. All right, what does that look like in the calculator? Well, it's menu. This is under probability and distributions. And we want a norm CDF. It asks us what's the lower bound, where our lower bound is 68. What's our upper bound? Well, it's 70. What's our mean? I believe that one was 64. And our standard deviation is 2.7. So norm CDF, lower bound, upper bound, mean, standard deviation. And the College Board very much would like you to document what these numbers represent: lower, upper, mean, standard deviation, and the probability, 0.0561. Now, there's a slight difference between those because there's some rounding. Of the two, the one off the calculator is a little bit more accurate. What's our conclusion? Our conclusion is the probability that a randomly chosen woman is between 68 inches and 70 inches in height, is 0.561. All right, that concludes all the stuff for section 6.1.